Hello, can you hear me?
Yes.
Hi everyone, can you hear me?
Yes,
Yeah.
we can.
Okay, so let's start. Um, we discussed let me we discussed polarization last time, but we did not go into detail like how we get the linear polarization, circular polarization, and elliptical polarization. So today we will talk about that. Okay. Okay. So let's say we have a field or electric field that is traveling in the negative z direction. So the component of the field are, okay, so there is a x component and y component. It could be theta and phi too, depending upon the coordinates you are working in. So it's x and y, and we know that we can also write these as, so x component can also be written as real part of ex minus e j omega t plus kz. Okay, and where this can also be written as e naught e j omega t plus kz plus phi x. So which means that first we are saying that E naught is the component, E naught is the general E, and EX is the component of that. Okay. And what we went by phi X, that it's the phase of the EX, right? And when we were talking about this, we were saying that let's say you have a signal that is propagating. So the phase is decided by the point the signal starts at any point. So it could be any point, it's instantaneous value. So let's say if we are talking about z is equals to 0, and so at z is equals to 0, here, if this is your cos signal, the phase is 0, right? But phi x. But if it is a sine signal, then it means that your phase is 90 degrees, right? So this is defined by the phase or the point where the signal starts. So we can also write this as, okay. So now the y component, we will write it the similar way. plus 5y, and this will be, so electric field is actually the combination of two components, x and y, right? In this scenario. And we are thinking that phi x and phi y are the two phases of the two components. Now, how do we know that these components are making it a linearly polarized signal or circularly polarized signal or elliptically polarized signal? We will know that. So if I move and I say, so what is linear polarization here? That they said that del phi is equals to phi y minus phi x is equals to n pi, where n is 0, 1, 2, 3, and so on. So the phase difference is equal to n pi. Then it will be a linearly polarized signal. Okay. 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 So now if we write it as we are given the equation, we can also write it like this. Ex will be, if I ignore for now, I am thinking that the magnitudes are equal. Ex naught is equals to Ey naught. Then Ex will be cos omega t plus kz plus phi x. And Ey will be cos omega t plus kz plus phi y, which I can also write cos omega t plus kz plus phi x plus n pi, right? And I can also write this as because this can come outside and I can write it this as my plus or minus. So this will become, so this is another way of writing it, right? So let's say if the unit vector associated with this was ax and unit vector associated with this was ay, then I can also write it like this. Is it clear? So when I am writing it as a combination, it will become right? So which shows that this thing is basically deciding the what you should say, that whether it's a linearly polarized or circularly polarized signal. So if you see right now, in this case, uh, X and Y components, we can say tan inverse AY over AX. So if they are, the magnitudes are equal, so then they will give us +1 means theta is equals to 45 degrees, right? Plus or minus. Now, if we plot it, right, how the phase is decided. So let's say we are saying t is equals to 0 and z is equals to 0. So in this case, the resultant vector will be drawn at 45 degrees. If it is plus 45, let's say. Now, if your t is equals to 0 and z is equals to lambda by 4, in this case, k is 2 pi by lambda into lambda by 4, pi by 2. So this will be 0. See what I'm doing? I am just trying to find out the phase here. So when t is equals to 0, z is equals to 0, this will become cos 0. This will become 1. And we already know the phase was 45, so we draw it like this. Now, in this case, when lambda by 4, I am doing cos this because t is equals to 0. So this will become cos pi by 2 and 0. Now, if I come again, this will be z is equals to lambda by 2. So in this case, at t is equals to 0, it will become lambda by 2 into 2 pi by lambda pi, so -1, which means 45 degrees. So this will be the phase. So I'm trying to say, because it's a linearly polarized signal, so that's why it will oscillate between 45 and -45 degrees. Okay? Means that, why I'm explaining all of this, because you were seeing, because you were seeing the phase movement when I was showing the slides, you were seeing the phase movement in that circularly polarized signal. So, I mean, the question arises how this phase signal moves, right? So for this linearly polarized signal, phase signal does not move in rotation, but it moves in the linear way, either 45 or -45, depending upon the magnitudes that they have. Now let's try to see that how the phases of circularly polarized signal moves. Okay. So circular polarization occur when you have the distance between, or the phase angle is I am writing for clockwise right now. I mean, so there are two types of polarization, clockwise and anti-clockwise. It depends upon the rotation. So if it is a clockwise rotation, this is the difference. And if it is anti-clockwise, this is the difference. Zero, 1, 2, and varies from 0, 1, 2. Okay, so I am taking one of the case. in which I am thinking that I think clockwise rotation, or it's also called as 1 minute. So this is your clockwise and this is your counterclockwise. This is called right hand and this is called left hand. Okay, so the difference I am taking is when my n is 0, I can take it as pi by 2. Okay. So now if I move and I draw it, my EX will be the same. But my EY will be and I can also write it as which makes it right. So when I am combining them, they become oh sorry. Because this was equal to and I replace phi y as phi x plus pi by 2. Does this make sense? Is it fine till now?
Dr. Collin, can you scroll up real fast? So there's a clockwise and counterclockwise solution, both equal to 1/2 plus 2n times pi.
Just a minute. Let me make. Yes, go ahead.
Oh, I was going to say, so both solutions for clockwise and counterclockwise both equal to 1/2 plus 2n times pi.
No. So this is minus 1 by 2 plus 2n pi, right? Which means that if this was the clockwise, so this is clockwise, right? If it is counterclockwise, it will be got it? So
Yeah.
there should be minus here. I don't know what happened to my voice. 1 minute. Hello, can you hear me? Can someone speak up?
Hear you.
I think I am hearing from here. 1 minute. Okay. Is it making sense? Who's asking the question? So does this make sense?
Oh yeah, it did. Thank you.
Okay. So now I am writing the phase for this one. Okay. So let's say I am taking t is equals to 0 and I'm progressing with z. So it means that I am taking a spatial propagation. Okay. So I'm saying for t is equals to 0, when your z is equals to 0, then what will happen to your phase? Okay. So it will be ax cos 0 plus ay sine 0, right? So it means that this would be 1. So I will have the phase here, like the total E. Now my t is equals to 0 and z is equals to lambda by 4. Then E will be ax cos 2 pi by lambda into lambda by 4 plus ay sine 2 pi by lambda into lambda by 4. It will become ax cos pi by 2 plus ay sine pi by 2, right? So this would be there, like, because it will be ay, right? Similarly, if I take t is equals to 0, z is equals to lambda by 2, it will become cos pi by, so 2 pi by lambda into lambda by 2 plus ay sine 2 pi by lambda into lambda by 2, and it will become minus ax plus ay 0. So it will become this way. So you can see the rotation of that, rotation of your vector, right? Similarly, if I take z3 lambda by 4, you should see zero minus ay. So it will become this, right? So if I am just plotting this, it is the total thing is rotation like this with z. Similarly, it rotates like that for the t as well. So that's why due to this rotation, we are getting circular wave. Does this make sense? Chris?
Yeah, I think so.
Isn't this the clockwise direction that we're doing here, though?
Yes.
Okay, thank you.
It looks anti-clockwise.
Yeah.
Actually, you know what? I think it's the receiving end and the transmitting end. So from one end, it's clockwise and other end, it's anti-clockwise. So they defined right hand or the plus thing as clockwise and the other thing as anti-clockwise. Okay, so I'm just sticking with that. Okay. Okay, so now we know why they are circular and why they are elliptical and why they are linear. So I just want to define, I will not go into details of that, but there is another polarization that is called elliptic polarization. And elliptic polarization is any other angle than linear and circular. So elliptic says del phi is equals to phi y minus phi x is equals to is not equals to, sorry, n by 2 pi plus minus n by 2 pi. And if this is greater than 0, this is clockwise. And if this is less than 0, this is counterclockwise. So it means that any other angle than circular and linear, that stays as elliptic polarization. And in elliptic polarization, your magnitudes are also not equal to each other. So if I just summarize all of them, I can write it as in linear polarization, it is possible that you have only one component of E, like either E is X directed or E is Y directed, or if you have two components, then they will be 180 degrees apart. So either there is only one component of E, or if two components they are in phase or 180 degree apart. In case of circular, they are all two orthogonal components. And the components have same magnitudes. And components have phase difference of odd multiples of 90 degrees. for elliptic polarization, the two components can have same or different magnitudes. Their time like their phase okay, so their phase difference is not 180 degrees or odd multiples of 90 degrees. So it's any other angle than this. Okay. So another thing I want to write is that ax plus jay, a theta plus j a phi, they are all written as right hand or clockwise. And ax minus j a phi or a theta minus j a phi. So this is y and this is phi. These are termed as left hand or counterclockwise. Like this is a convention they are using. So, one more thing I wanted to ask. So there is no lecture on Thursday, right?
I think on Thursday, yeah.
Okay, so we are not having a lecture on Thursday. Then there will be a lecture on Monday, right? And then we will have one more thing I want to just see. So no lecture on Thursday, but there is a lecture on Monday, and then we have a midterm on 25th. So I will post a homework before like the Thursday lecture. But what I will do is it's kind of the practice homework. So I will post the solutions. So it will not be, the graded one. Okay. So I will post the solution before your midterm. And what I will do, I will post all this, like the solution of all the homework problems, right? Irrespective of those, whether they are in your homework or not. Let's say what I'm trying to say, let's say I have given you 2.32 problem in your homework number 2. So I will post the solution of the problems till 2.32. Okay. So you will have all the solutions before midterm. I know it's hard to do all of the problems, but I mean, it just gives you the sense that how these solutions are being done. Okay. So I will post another practice homework before that so that it will help you guys to, so we may not be able to finish the whole of chapter 2, but major part of that we have finished. So I will tell you on Monday till which topic we will include it in the exam.
Hey, Professor,
Yeah.
just had a quick question. So for the exam, would we be able to have a formula sheet or no?
Yes.
Okay. Is it like open notes or is it just a formula sheet only?
I will give a formula sheet, I think.
Okay, thank you.
I will try to give all the integrals, okay? And I will also try to give the difficult ones, which are included in your book. But I may be telling you on Monday what is the formula sheet looks like, okay?
Great, thank you so much.
Yeah. So now, as we have done the polarizations, we will check the polarization loss vector. So what we are trying to say here is that if there is a transmitting antenna and there is a receiving antenna, okay, so transmitting antennas polarization is defined as rho W. So this is a polarization unit vector, you can say. And receiving antennas polarization is defined as rho A. So what is polarization loss vector is that if your incoming waves polarization is not exactly the same as your receiving waves polarization, right? Then there is some mismatch between them, and that can cause a loss in the signal. Means that if this was your circular polarized wave, but here this is a linearly polarized signal that can only receive vertical polarized waves. So what happens is that this wave will lose the horizontal polarized signal, right? And only vertical will go here. So there is a loss at the receiving end of the signal. So that what we are saying is, so if this is a vertically polarized antenna. So that is so we need to find out how much signal we are losing and what is our polarization loss factor here. So for that, polarization loss factor is the dot product of the polarization vectors of the transmitting and receiving signal. Okay, so the dot product means that if they are of the unit vector, like the unit magnitude, it will be the angle between both of these vectors. So if this is W and this is A, so this will be the angle. So if they are in the same phase, it means that they will have the one, like the polarization loss vector is one, which is the best case scenario. But if they are like the perpendicular to each other, means that antenna cannot receive anything. So this is the polarization loss vector, or another way of describing it as so if this is the or if this is your like rho W, this is your rho A, both are in phase, then it's one, right? And similarly, sorry, here there is a square. Similarly, if this is your phase, I'm just drawing the imaginary thing that if they are having some angle in it, so this will be and if they are orthogonal to each other, the dot product will be 0. So that's how we defined it as the loss that is happening at the receiving end. I will solve a problem so that it will make more sense. So the problem states in 2.11 that you have an electric field example, that you have an electric field linearly polarized wave EI is equal to AX E naught XY E minus JKZ propagating in the plus Z direction. And it's incident upon the linearly polarized antenna, but the antenna's polarization is in the two, now like the directions. Like it has two components, Y and X, and this is R theta phi. I mean, it's just they wrote it like that, but it is like they give us these components, so we are okay. Okay. So we have to find PLF, like the polarization loss vector. So we will say that in this case, PW is AX AY by square root of 2 because it's a unit vector. So unit vector is the vectors divided by their magnitude. So polarization loss vector is so what I should write here. So what is AX dot AX?
That'd be 1.
Yes. And what is AX dot AY?
0.
Yes. So this will become like that. So it means that it received a half of the signal and half is not received, right? So the polarization loss vector is half, and if you are calculating it in dBs, it is okay. So another example is given in your book, that is 2.12. I just want to talk a little bit about it. So in this example, they are saying, I mean, if you have a book in front of you, I cannot just write all of it. I just read it, okay? So it says a right-hand circularly polarized wave radiated by an antenna placed at some distance away from the origin of a spherical coordinate systems is traveling in the inward radial direction at an angle theta phi, and it is impinging on a right-hand circularly polarized receive antenna placed at the origin. So I just draw it what they are saying. So they are saying, so there is right-hand circularly polarized wave that is going out of the antenna, and there is a receiving antenna that is also right-hand circularly polarized, but it is at the receiving end. So the difference is that in this antenna, if you are saying that in this antenna, the polarization vector that is transmitting is this. Now, this is a receiving end. So because this is a receiving antenna, but it is the right-hand circularly polarized, but with respect to transmitter, it appears as this. Okay, so it's like that you have the reference that you are looking at. So if you are looking at from here, this is circularly polarized in one direction, right? And if I am at the transmitter side, the other antenna, which is this way in its own reference, it will appear to me the other way if I take myself as a reference, right? It's kind of the mirror thing that you're observing. That's why both are right and circularly polarized, but this is transmitter and this is receiver. So when we are writing these unit vectors, we are taking one thing as a reference. Okay? So that's why they wrote it like this. Is it clear? Okay. So now I will talk about input impedance. I think we touched upon that in the very first lecture, but there were some questions, there were some things that we have touched. We did not do it completely. So here we are doing it a little bit more in details, okay? So I am doing input impedance. So previously I drew the equivalent circuit of antenna. So if this is my antenna, this is generator, this is antenna, and here from here antenna is starting. So this is the point A and B. Okay, and this is a transmitting mode. It's very important now as you are moving more towards deeper, like you are digging deeper, you will know that we will differentiate them in transmitting and receiving modes. So this is a transmitting mode, and equivalent circuit of this antenna will be RG, VG, RG, XG. So this is the resistance and the voltages of the generator side. On antenna side, there are RL, load resistance, RR, radiation resistance, and XA, antenna reactance. What it is, we will discuss that. So there is a current that is flowing in the equivalent circuit, that is IG, I think, right? So I will write it as, so for this antenna, ZA is equal to RA plus JXA, right? Which means that this thing is RA, antenna resistance. So the impedance of antenna is equal to RA plus JXA, where your RA is RR plus RL, which is load resistance, and this is radiation resistance. Sorry, not load, it's a loss. Sorry. So this is a loss. Why I was saying that, why they have both resistance. So this is a loss resistance. Okay, so this is a loss that antenna carries. Okay. Now your ZG is RG plus XG, where these are resistance of generator or the source, you can say. Source or generator resistance. This is source or generator reactance. Okay. Now the current will be VG by ZG plus ZA, which will make it VG by RG plus RR plus RL plus J XG plus XA. We are good till here? Josh?
Yeah, this makes sense.
Okay. Now we need to know that how much power we are transmitting in, like, from antenna. Okay, and how much it is lost, how much we are generating. So to know all of this, we know we have to write the power formulas. So what I'm saying is power delivered to antenna. Because RL is a loss resistance, so the power is delivered only through RR, that is radiation resistance. So that's why the power delivered to antenna is, or like the only useful power that is radiated is RR. So you will write okay, so the magnitude of this is, sorry, so this magnitude of this. Sorry. I should not make it difficult. First, I should write, so this needs the magnitude of IG square, And the magnitude of IG square is okay. So when I will write it here, it will become so that is the radiation, like the power delivered to the antenna. Okay, so now the power dissipated as a heat is in the loss resistance. Okay, so the power dissipated as heat is the LPL. That will be the same thing with RL. Okay, and as we have another resistance, that is RG. So we are saying that PG is 1/2 VG square RG RR plus RG plus RL square plus XG plus XA square, where this is power dissipated in internal resistance.
Dr. Khan,
Yeah.
how do you go from RR as a numerator to RL?
Okay, that's a good question. So what we are doing is we are calculating dissipation or the like the power dissipation in all these resistances. So first we did this. No, first we did RR, then RL, and then RG. So when you calculate the dissipation, it's I square R, right?
Yeah.
So that's what we have done here. So, okay, sorry, I meant here is, this is PL. PL is equals to 1/2 VG So you can, sorry, write it as IG square RL, okay? And then this is PG, which will be 1/2 IG square RG. So these are the power dissipations that I have calculated across these resistances. Got it?
So so R is the power delivered to which one? To the source?
Okay, so what I'm saying here is, if you see here, that, so you know the real components are the real powers, right? And the imaginary components are the stored energy, right? We know that. So XA and XG, we are not considering because they are reactances, they are restored energy. The only real power that we are considering is across resistances. So what we are saying that what are the power dissipations or the delivered across antenna? Because RG and RR are your resistances that are lost, like the RL, we said that it's a loss resistance, and RG is a generator's internal resistance. So they are the power dissipations, we said. But RR is the radiation resistance. That is the power delivered to antenna. Like that's the power that is transmitting. If it is in the transmitting mode, that is transmitting outside. Okay. So it means that if you are considering this as an antenna, so the equivalent, so if this is your antenna, the equivalent resistance or equivalent circuit of this antenna has losses in it, has like the other factors in it, and we are taking them into account to know that how much power is exactly delivered to antenna. It's not that what you have transmitted will be delivered. So there are some loss factors that we have to take into account. Is it clear, Jonathan?
Yeah, thank you.
Okay. So we are here. Okay, now, so these are the power delivered or power dissipation or stuff like that. But what is the power supplied? How we calculate the power supplied? So power supplied is one over 2 VG IG conjugate, and it is here your IG is what should be your IG? VG conjugate by, sorry, I need to see that. So here your IG is VG by ZG plus ZA, right? So I will write it ZG plus ZA. And that will be JXG plus RR plus RL plus JXA. Now, because this is a conjugate matching scenario, so it will be minus JXA. And these will cancel out with each other. Or wait a minute, just write this. Don't write this at all. So this is your power supplied, okay? I just don't want to put anything here. But this is your power supplied where it's VGIG and half VGIG. So we will get rid of the conjugate scenario as well. So this is the power supplied, and those are the power dissipations or delivered to antenna. Now we are tackling a special case where we want to see that what is the maximum power that can be delivered to antenna. Okay, so we need to know that what is the best case scenario in case of antenna. So we will do that. So we can say best case scenario or maximum power that can be delivered to antenna. And we said that this is power supplied. If you have noticed, when we have calculated the power dissipations or power delivered, we included R because that's where the power is dissipated or delivered. But when we are calculating supplied, we are calculating the source current and the voltages. Okay, so the maximum best case scenario or the maximum power delivered to antenna, we need to know that. And for the best case scenario occurs when there is a conjugate matching. Okay. Sorry. Which means that in the conjugate matching scenario, your RR plus RL is RG, and your XG is minus XA, or you can also say RG is RA. So in this scenario, the maximum power can be delivered. Okay, so when you plug this in all the above equations, like let's plug this in PR first. PR will be if I go up here, so this will go away because XG is equals to minus XA. And this will be RR plus RL. So this will become 2RR plus RL. So I can write this as so this is your conjugate matching scenario. Okay. And if I replace the same thing in PL as well, it will also become like this. And the only difference will be RL here. PR, PL, and PG is a little bit different. Let me see what is the difference. Okay. Okay, so in the PG case, it will become which can also be written as okay. So I will just write one more expression and we will continue it next time. But this power supplied will be in the conjugate matching scenario, which I was writing before, was this. So in the conjugate matching scenario, you will have current as ZA plus ZG, where this is your RR plus RL plus XA, JXA, plus here RG plus JXG, because this is conjugate matching scenario. Here you will have minus JXA. So they will cancel each other and you will have RR plus RL plus RR plus RL, because RG can also be written as that. And this will be two RR plus RL into 2. That is 4. So that is your power supplied. I will stop here and we will continue next time from the next part. One thing I want to mention regarding problem 2.8, I think there was some miscommunication on last time. I'm just quickly want to address that. So in problem 2.8, in your, like the problem suggests that you have to convert from E to U. We are done with this? Can I move?
Yeah, you can move.
Okay, So in problem 2.8, the only thing that I want to just clarify, I think Ria asked, that E is E theta EA sine 1.5 theta E minus JKR by R. So she asked that how you are converting it to U, right? So I think in the 2.19 equation and 2.27 equation that your U is equals to R square E over 2 eta. R square E square by 2 eta, right? Let me just quickly confirm. Sorry, so it's not R square. It's just E square over 2 eta in 2.19. U is equals to that. So when you plug this thing in here, and you said that this is E sine 1.5 theta E minus JKR by R square by 2 eta, right? So when we are taking U, we are taking as it is as a normalized U. Or so when we are taking it as a normalized U, our this part, which is not dependent on theta or phi, over which we are concerned with, this part and this part will become normalized. So you will just have then, or this as well. So you will just have then sine 1.5 theta square, which will be sine cube theta. So this is due to the normalized version of the U. So that's where your magnitudes are going, okay? So whenever you are taking U, you are just taking the by a square of the theta or phi dependence thing, because that's the normalized U, or that's the where your magnitude is being normalized. Okay. Sounds good. And thank you very much. It's full time today. And Erin, if you want to stay around, you can, and bye
Yeah.
for everyone else. Thank you.
Thank you. Have a good
Thank
one.
you. Have a good one.
Bye.
Thank you.
So that